Okay, now for the really cool part. We are going to actually create some decision trees, do some decision tree learning using Python. So the package that we're going to use for this and for a lot of our learning going forward is called SKLearn. Here's the homepage of it. It's abbreviated SKLearn. So if you go to sklearn.org, you get here. It's already installed if you have Anaconda. There's a bunch of stuff here. There's some tutorials. I believe I usually go to the user guide for what I want to do. Let me just go out a little bit. So we are in supervised learning right now, and you can see there's nearest neighbors here. There's decision trees here. There's neural network models. There's a bunch of stuff that we're going to look at here. Later on, we'll look at some unsupervised learning as well. But right now, we're in section 1 here. So we're looking at decision trees today. And you can see the documentation's pretty good. It sort of goes through how decision tree models work, advantages and disadvantages. You don't have to go through this stuff yourself. I've sort of given you what you need to know in the handout. But then it goes and tells you how to use the various objects that are involved in sklearn. So this part of the documentation I'm going to walk you through today. I've put links to things that you need for this in here. So built-in data sets, creating and training a decision tree, optional parameters, and this one to WebGraphViz, which you probably don't need, but I'm leaving it in there just in case. What we're going to do is and by the way, this module you're looking at here is my version of the module. So it has some hidden things in there. It'll look a bit different when you get there. We've gone over this handout here, and we're going to take a look at some of the example code. So inside the example code folder, you will find this file, decisiontrees.py. And if you run this, well, you'll get an error the first time because there's an installation you have to do first. But this file, this program, what it does is it loads a data set, one of the sklearn built-in data sets. So you'll be loading your data from a file for the assignments, but sklearn has a bunch of built-in data sets, so you don't have to go to a file and load them in. Then it splits it into a testing and a training set, and it runs a decision tree on it, and then graphs the result. And it's the graphing of the result part that we have to install an extra package for, and fortunately for us, Anaconda makes it really easy to do that. So you go conda install, you just copy that and paste it over here. Now I've already installed it on my machine, so I can't show you what it will look like, but you'll get this collecting package metadata. There'll be a big pause at first as it runs the conda software, more than there is here. And then what will happen is you'll get a whole blast of really badly formatted text, which will end with a question, yes or no. Just type Y and hit enter and keep your fingers crossed, and hopefully everything will go well and you will have the Python GraphViz package installed. So you might want to actually pause the video now and do that, and then come back. If for some reason you can't get Python GraphViz installed, there is an alternate that doesn't use Python GraphViz, and I will go over that at the end of this when I've gone over everything else. Okay, so there's a fallback position if you can't get Python GraphViz installed properly. Okay, so first thing we're going to do here is we import NumPy, and then we get the data sets. So from sklearn, which is the name of the package, which is already installed, we import the datasets module, and then from there you can create a data set, or you can retrieve a data set. So dataset equals datasets dot, and you can see these load methods here. Each one of these loads a different set, a very standard set of data. So the iris data is in here, as well as the Wisconsin breast cancer data, which I'll use here. Load breast cancer. So this is another one that's available on the UCI machine learning repository, is the breast cancer data. So doing that loads it. What you get is, I think, a dictionary. Hang on. Or maybe it's a different kind of object. Yeah, it's a special kind of object called a bunch. But there are a few things that you can use to access it, and I've given them to you here. Dataset.data, that's the data array. So you can see it here, and you can see the ... It's quite a big array. If you want to know how big it is, you can use the shape field, And you can see that it's got 569 rows and 30 columns. Now this data set, I believe it's ultrasound measurements of potential tumors, potential cancerous tumors, malignant tumors. And there's a bunch of measurements of them. There's 30 measurements. And the classifications, the targets, so if we do dataset dot, where are we? I think it's target. So this is what we've been calling labels, class labels. So this is a related array, of course, between the target labels and the data. So row 1 here is not malignant, 0. Whereas, and most of the first few are not malignant. The very last one, so the last row, which is right here, this does represent a malignant tumor. So it's benign or malignant. Those are the two class labels. The other information that you can get out of this are feature names. Whoops, it's not a function. So here are your feature names. So the first feature, so up here in the data, this feature here, the first one in each row is mean radius. The second one is mean texture, mean perimeter, and so on. So these are the names of the measurements. And let's see what else we can get here. Dataset dot. I think you can get target names too. Not all the data sets have all of this information in them. It depends on the data set. But you see the target names are malignant and benign. So that's class 0 is malignant, class 1 is benign. If there was a third class, it would be class 2, and it would be the third one in here. Okay, so that's all the information about the information. That's all the information about the information. That's all the information about the data sets. I can also pull out the iris one, for example. Datasets.load. They all start load. Oops. Load iris, bracket, bracket, and then iris.data. There's the data there. Iris.target. That's the target array. There's 3 classes here. Iris.target names says that class 0 is setosa, class 1 is versicolor, class 2 is virginica. So that's yeah, that's how it works. Oh, and here's the feature names as well. So sepal length, sepal width, petal length, petal width. Okay, so that's nice. That's a handy convenience. We've got these data sets that are already built in that we don't have to load them or clean them up or anything. Everything is prepared for us. So first thing I do is load the breast cancer data set here, and you could easily change this to iris and then do it with iris. And if you want more info on it, here's the link, but there's also a link in here to built-in data sets. Whoops, hang on. I'm going to right-click that and say Open Link in New Tab. So here it is. This gives you examples loading iris. There's some handwritten digit data that you can get, and it talks to you about how the data is all put together, how it's represented. Okay, the next thing in here, yeah, this is actually a link to just generic supervised learning. I don't think I put a link in the course materials to it. So if I paste this in here, this is just a general discussion of how supervised learning works, and the importance of a training set and a testing set and so on. Okay, so so that's just general information about that. Hopefully by this time you guys are starting to get comfortable with the whole idea of a with the whole idea of testing and training sets. Sorry, I was just looking at my code here. So what I'm doing here is I'm creating a random permutation. So this is like using a shuffle, but I'm doing it a different way than I showed you before. Oh, that's nice. Look at that. It auto-imported NP for me because I forgot. So if you go NP random permutation, let's say 10, you get the numbers from 0 to 9 randomly permuted. So that's actually better than what I showed you guys before. I should probably put that in the handouts. That's like doing an A range and then doing a shuffle of the A range. So you get a random permutation. So I'm saying give me a random permutation with all the indexes that would go into the data set. And then I'm just going to do an 80% 20% split. So my split is I get the length of the indices here. So that gets me this length times 0.8, and I round it because otherwise it'll be a decimal number and I don't want that. And that's my split point. And then I split the indices into the first half here and the second half here. So I'm taking this index array and I'm passing it into passing it in as an index array to the data and the targets, and that gets me 4 arrays. I've got the training data, which is the first part of the data. So this is the random permutation. So every time I run this, indices is going to be a different random permutation of indices. Indices is the plural of index, the correct plural of index. So I'm splitting it. The first 80% are going to be training data. And then I go to the targets, which is the related array. I sort it in the same way. I rearrange it in the same way, but I take the first part of the data, and then I take the last part of the data to be the testing and the testing target arrays. So for you guys, this code, you can probably adapt this code pretty directly to what you're doing, but you will have to, this step here is going to be where you will have to read your files in the assignment. Then I create a decision tree object. So what I do is from SKLearn, I'm importing the object, the package that I want, which is the tree package. Now this is all discussed here. So again, there is a link to it. This one has a link, I believe, right here, creating and training a decision tree. If I open that in a new tab, I get this, which I think is the same as this. Yeah. Same as the link there. So here you go, SKLearn import tree. You create a decision tree classifier, and then you call its fit method and to train it, and its predict method to test it. Okay, so that's the basic idea. Is you're going to, and this will be the same for all the classified learning, the supervised learning activities that we do. You will create the classifier object. You will call its fit method to train it, and you will call its predict method to test it. Okay, so pretty straightforward actually. Once you've understood it. So what we're using is an object called decision tree classifier, and we'll take a look at that object in a moment. We'll take a look at the API for that object in a moment. So CLF stands for classifier. So I say, okay, create my classifier. This actually this instantiates an object. When you have a class in Python. So the decision tree classifier is a class, like a Python object-oriented class. You can tell because it starts with a capital D. And when you run a class name as a function, it creates an object. It's like saying new decision tree classifier in other languages. So this creates our classifier object. And then we call the fit method. And this is the same no matter what classifier you've got. This is going to be the same. You have to pass it the training data and the labels, the targets. So train data, after I run, let me run this thing actually. I'm going to run it. Let it do its thing. We'll look at the output in a second, but we've got, after I run it, we have train, which is the training data, and test, which is the testing data. So train.shape, that's got 455 rows, test.shape has 114 rows. And every time I run it, you can try this, you can run it again and look at the train data, and you should see the first few examples here should not be the same ones because we're using a different permutation every time. So each one has 30 columns, of course, and then we've got the train target, which contains the labels. Okay, so slight terminology shift here because SKLearn calls the labels or the classes, calls them targets. So these are the correct classifications that go along with the training data. So I just go clf.fit and boom, it's done. It's fitted itself. So clf.fit train, train target, like that. Actually it returns a new classifier. So I'm doing clf equals clf.fit. So now clf is trained, and I can go clf.predict, and for this one I give it, well, I'm doing two things here. If you look at the output, I'm giving you the accuracy on the training data and then the accuracy on the testing data. So by default, the SKLearn classifier, remember how we talked about decision trees can keep splitting and splitting until they achieve 100% accuracy on the training data? That's not a problem for a decision tree classifier. So by default, that's what they do. So this has gone to 100% on the training data. But testing data, it's only getting about 88% accuracy, which is still amazing. This is known to be not too hard of a data set, but it's a benchmarking one. For that accuracy on real-world data, that's really, really good accuracy. But here's what happens when we call predict. It returns basically my testing array. It returns an array of predictions using the model that it generated when I called fit. So I called fit, and it generates a decision tree, which we haven't seen yet. It's kind of keeping it to itself. It's inside of its guts. And then when we go predict, it runs the testing examples through the decision tree and comes out with a classification, either 1 for malignant or 0 for benign. And then we can, basically what we need to do now is compare that to the test target array. So you can see right away, just to eyeball it, it got the first one wrong. Say this was its prediction, and this is what it should have been. Second one it got right, third, fourth, fifth got right. So you'll see most of them are correct because it's getting 88% accuracy, but if you look through it carefully, you should be able to see a few places where, like right here, the arrays aren't quite the same. So it's getting it wrong. It's making a few mistakes. How do you quantify that? Well, if you've got your predictions, CLF.predict, let's do this again. So we've got our predictions and we got our test target. You can do stuff like this. Predictions equals test target. That gets you a bunch of trues and falses. And here's a little trick. If you call sum on that array, it's going to add up. Hang on, let's just take a look, make sure this is working. Yeah, so the length of the predictions array is 114. When you sum up a Boolean array, it takes trues to be 1 and falses to be 0. So we're seeing a false here wherever the arrays didn't match. So falses represent wrong predictions, trues represent correct predictions. So we just sum them up, and we can just simply do sum, hang on, the sum divided by the length times 100, because to make it a percent gives us the accuracy, 88.5%. And I think that's probably what I'm doing down here. I'm doing it in a couple steps. I'm saying correct equals, number correct equals prediction equals test target. I used the dot sum method here. The one I showed you here, I used the, I used the global function, but here I'm using the method. They do the same thing. And that's it. Pretty cool, huh? So that's how you're going to train and test classifiers. Now you're going to do this over and over again. You're going to do multiple splits, create different training and test sets from the data that you've got, and then come up with an average performance on the test set. You're also going to mess around with a lot of possible parameters, because right now here we just created with the default parameters. We didn't pass. There's a bunch of named parameters you can pass in here that will change the performance of the system. But before we get to that, let's just take a look at this code here. You can just copy and paste this code. If you've done the conda install step that we did at the beginning and it worked, this should work. And what it's doing is it is using the GraphViz package to create a tree representation, and it renders it as tree dot dot. So that is over here under wherever you had your code. So I was in week 5 example code. Here's my example code. I don't know if you can see, this matches pretty much my timestamp here. It's created these two files, tree.dot and tree.pdf. Tree.dot is not a Word file. If you edit it with Notepad++, it is a text representation of the tree that it created. So this is its own little GraphViz language for creating a graph. Tree.dot.pdf is the one that we want, the nicely rendered one. So here's how it looks. Okay, a few things to look at. First of all, this is the top of the decision tree. This is the feature name for the first feature. Now, what you want is, when you're doing this, you're going to have to change some things here. So hopefully you're going to have an array of feature names. I just used dataset.featurenames, and hopefully you're going to have an array of class names. So you need to make sure that you have that and that it's correct here, and that it matches. It has to match the actual column 0 name has to be correct, column 1 name has to be correct, or else your tree isn't going to look right. If you don't put this in, it'll just replace this with some generic text like feature 1, feature 2, and so on. So you do have to do that with it. And yeah, there's the classifier. Everything else you can fill in the way that it is. There's the classifier, and there's the feature names and class names if you have them. So you have to customize that. And then you get this. So it's saying I'm using the feature worst perimeter, and I'm asking is it less than or equal to this value? If it is, we go over here. If not, we go over here. Now there's a bunch of other things going on here. This is the Gini probability or improbability, I think they call it. This is the default measurement of how good this set of data is. So all the data in there, the Gini, basically represents the chance that you would be correct if you gave it a random classification. I think I have to look that up, but it's 0.462 is not good. We want to go to 0. So it's a chance that you would be incorrect. So 46% chance of being incorrect if we tried to just put a categorization on things in the whole area. There are 455 examples, and they split like this. 165 are in the malignant class, and 290 are in the benign class. That's why it says class benign down here, and it's color-coded it. You'll see everywhere where it says class benign, it'll be some shade of blue. The darker the shade, the more the dominance of the benign, right? So this is light blue because it's got a Gini of 0.462. It's not as pure. This split over here, so what it's done is it's created a much purer split over here with only 12 malignant examples and 269 benign examples here. That's why it's a darker blue. There's only 281 samples here, and the other 174 went over here. Right? So, and then over here we use worst concave points, and then we get it down even further. We split it even further. So now we split off, there's only 8 samples on this side, and 273 of the 281 samples on this side. So this just shaved off a few points, but it made the classes more pure. This one has now a Gini of 0.043. So you're getting better. You want to go down to 0 here on this measure. Here the Gini's gone up a little bit, but there's a small amount of data there, and the next split creates 2 pure sets. So they find a split which is symmetry error less than 0.02, which results in the 6 malignant examples going on this side and the 2 benign examples going on this side. So true is always to the left here, false is to the right. Okay, and this, as you can see, this is a pretty bushy tree, but even the longest path in it, one step, 2, 3, 4, 5, 6, 7, 8 steps from the, it's got a depth of 8, this tree, and so that's going to be super fast to classify. Even if we end up down at one of these nodes down here, it's basically 8 if statements to get the classification. There's one white thing in here. That's white because it's evenly split between malignant and benign. And then so that's easy to split off. As long as these are not the same point, as long as they have different values, you should easily be able to find a split point that separates them, unless they're identical and they've been labeled opposite, in which case there's probably a problem with your data. Okay, so that's easy to split off. So that's what your tree looks like. This is a nice printout of your tree. Now, let me just say, what are you going to do if this doesn't work? It's like you try to import and it doesn't work. There is an alternative, which is if you uncomment these lines, this just gets you the first of the 2 files. So the first of the 2 files was, do I still have it? Yeah, this one here. And what you can do is you can go to webgraphviz.com, which is the last link here. Open a new tab and paste your output in here. So the output is definitely going to work, even if the other parts of it don't work. I just paste your output into here and go generate graph, and it's going to give you this. Oh, you know what? I shouldn't use the graph that I generated my way. I should use this graph. So I'm going to uncomment this. I need to do it this way because the features are different here. So I'm going to go Control R, uncomments, or comments out. And I'm going to run this again. Oh, okay. Try this again. There we go. Okay, I'm going to fix that before I give you the code. Sorry about that. I think things changed since the first time that I did this. Let's see if it works for me now. So I'm going to go into tree dot dot. I'm going to reload it here, copy it, go back to my thing here, paste. So this is the webgraphviz.com site. There we go. That's what I wanted. Okay. So it's not as nice looking, but all the information is there. And you can verify it's the same tree. Worst perimeter is here, the Gini measure, the samples, and the class. It's not as nice to look at, but it does work. And for including it in your reports, you'll probably have to do a screen cap because this is made in some fancy way. So I think you're not going to be able to copy and paste it in. It's not just an image you can take. You'll have to do a screen capture of it and put it into your report that way. So I'm hoping that most of you don't have to do this. I will fix this code over here so that it works. I'm going to comment it back out again. And I'm going to get this back. Make sure I can still run this. Oh, this will happen if you have your PDF open. So I've got my PDF open here. I need to close it. At least it happens with mine. It might not happen if you just have the reader. So there we go. So it's generating trees. Okay, so that's the basics. Now the only thing to do next is to take a look at how you can tweak the trees. Because just like with KNN, I want you to try different versions and try and take whatever your data is, try and squeeze the best performance that you can out of the decision tree. And there's two basic ways you can change the decision tree. One is you can change the way it decides on what the best split is. So you can change that from Gini to entropy. There's two options. And the other, there's a whole pile of other ways you can tweak the tree, but they're all about when do we stop. So you can see that, as I showed you, by default, we will go all the way down as far as we need to get it 100% accurate on the training data. So for example, down here, there were only 3 samples, but we split it anyway, rather than just saying this is malignant. And now we have an area which we say is benign, but the support for that is pretty low because we only have one example in this area. So remember, we're making boxes and boxes and boxes. Now we've got this box. It only had one thing in it. We might be overfitting. We might end up, this might be an outlier point. It might have been better to stop here and just say malignant. Or it might have been even better actually to stop up here where we had 15 benign and 2 malignant and say benign and not split any further. Okay, so there's a bunch of ways that you can look at. The other thing too is this is a pretty big tree, and if your data is more complicated, you can end up with a massive, massive tree, and it becomes less easy to interpret what the tree is doing the bigger the tree is. So there's other reasons why you might want to limit the overall size of the tree to keep it from getting too big and too unwieldy for you to interpret. So let's go take a look at the at where we can tweak it. And oh yeah, I have some suggestions here for you. Try these optional keyword parameters: criterion, splitter, max depth, etc. So if I copy this, this is also linked to from here, optional decision tree parameters. That's where I'm sending you to. That's over here. Now what this is this is the API for the decision tree classifier object. So sklearn.tree.decision tree classifier. And the first thing that it shows you here is the optional named parameters that are available to you when you are creating a new decision tree object. And then it explains them down here. So the first one is criterion by default is set to Gini. So this is how it decides on the best split. So you can use Gini impurity. Sorry, not improbability. I said improbability before. It's impurity. So you want impurity to be 0. 1 is maximally impure, 0 is what you're aiming for. The other one is entropy. Entropy is an older and more traditional way of doing the measurement of how good a split is, and it's based in information theory, which is a little mathematical subfield of computer science. The basic idea is how much if you don't do any work, you just have this big set of 455 examples, you're going to have to label each example separately. So that's going to take a lot of bits of data to create all those labels. But then if I split it this way, now I've got a pretty pure sample here over here and a pretty pure sample over there. I can label this whole sample, for example, benign, and then just label the exceptional points, the ones that don't fit. So I'm reducing the amount of information that I need in order to be, at every split, I'm reducing the amount of information I need in order to be able to specify each of the points. So when you start, you can label them all, I think benign, because that's what most of them are, and then just just have one label for benign, unless it's one of these points, and then enumerate all the points. Then the more you split, the more you can save space by just saying this whole region is benign, this whole region is malignant, except for this one point, which is benign. So entropy is measuring the amount of information gain, meaning the smaller and smaller the description gets that you need to in order to be able to label all the points. So that's the first thing that you can do. We could try criterion equals. If you want Gini, you don't have to put it, but if you want to change it to entropy, you can do this here. Now let's take this tree and save it as maybe call it tree 2. Rather than changing the code, I'll rename it over here. Oops, tree Gini. There we go. And I'm going to do this again, now having changed the criterion to entropy, and we'll see what the tree looks like now. So now I have two files. This is tree.pdf, which my code just produced. And here's the first tree where I used the Gini criterion. I guess I'll have to just switch back and forth here. So in Gini, it starts with worst perimeter less than 1.14. Not that different with entropy. It looks at worst perimeter less. It's got a different cut point. So it's making a different cut here. Then down here, it uses worst smoothness and worst concavity with entropy, but with Gini it used worst concave points and worst compactness. So it gets different from that point on, and you can see the overall shape of the two trees is quite different. Now they're both going to get 100% on the training data because we haven't throttled it back yet, but they might get a different accuracy. So this one, you have to run it a few times. You can't go with one run. Whoops, that's because I still have the trees open here. I'll close them. So, but this time it got 94% accuracy on the training data, then 92. Looks like it's pretty consistently, depending, no matter what the split, getting answers in the 90s. If I change this back to Gini, though, oh yeah, maybe it's going to do about the same. The first run was only 88%. Oh wow. So you'd have to run this a bunch of times, maybe 10 times, 50 times, take the average and see if there's any difference in the accuracy on the testing data between Gini and entropy. Let's leave entropy there. Okay, let's take a look at some of the other parameters. I'm not going to go over all of them. I'm going to let you guys go over them. So splitter is, I wouldn't experiment with that on small data sets. On large data sets, it could speed you up quite a bit. So the big slowdown step in creating decision trees is the fact that it's going to search exhaustively through every possible split looking for the best one. A different strategy is to use a random split. So best split is the default, so that's going to be the slow one. But you can get pretty good behavior by choosing random splits. You'll get a different looking tree, but it might still do quite well. So the idea here is instead of exhaustively trying every single split, there might be a million possibilities depending on your data set size. Just choose, let's say, 1,000. So some small number. Take 1,000 just random splits. So randomly choose a feature, choose a value, and then take the best of those random splits. And that can often get you a pretty good tree much, much faster than you would otherwise use. So let's try it. Splitter equals random and see what that tree looks like. Okay, it still gets us pretty, it's always going to go to 100% accuracy unless we tell it not to on the training. Testing data accuracy is not bad. Let's see if how the tree looks. Oops, oopsie. It's a bushier tree. It had to do more work because it wasn't using the best split each time, so it had to end up doing more splits. It starts with worst radius, whereas Genie, with the default parameters, started with worst perimeter. So it's quite a different tree. It's quite a bit bigger than the Genie tree, but it ends up doing, you know, by the looks of it, about as well. So I wouldn't bother with that one though. That's not a good one. It's not really about changing the behavior of the tree. It's about making it go faster and maybe getting a slightly suboptimal solution, but the trade-off is it's way faster. So if you find that it's taking hours to generate your decision trees because your data is so big, you could use the random splitter. The rest of these that I've got here have to do with limiting the tree. So one way to limit it is to say, don't let the tree get deeper than, say, 3 items deep. So if you look at, let me close this one. If you look at this one, it's got a depth of 1, 2, 3, 4, 5, 6, 7. It's got a depth of 8. So let's not throttle it too much. Let's say no going deeper than 4. Now it will, at this point, it's not a greedy algorithm anymore. It will backtrack and it's going to try and do some magic to try and find the best tree that doesn't go deeper than 4. And you can see that when we do that, we lose some accuracy on the training data. But the hope is that maybe because we are forcing it to make a smaller tree, it's going to have to make some more generalizations and it may not overfit as much. Now you're not going to see much in this data because this is such an easy data set anyway. But you can see it's still getting 92% and it's limited itself to 1, 2, 3, 4 steps through the tree. So we're getting a much smaller tree now. What if we said max depth equals, I don't know, 3? What would it look like then? Oops, I'm going to get an error because I left my file open. Still does pretty good. Still does surprisingly well, and produces an even smaller tree. So an even smaller tree, even this tiny little tree with just a few cuts, does really well on the training data. 94% here on the training and testing split that we used. The other parameters that you can mess around with are min sample split, which is the minimum number of samples that you need. Samples are examples, so the minimum number of points in order for you to split it. So if you set that to 10, if it sees 9 or fewer points in an area, it won't recursively split it. It'll just apply the label. So let's do that. Let's say min samples split equals 10. So we shouldn't see any leaf nodes in the tree. We shouldn't see any splits on samples that are bigger than, that are 10 or bigger. So if we take a look in here, you can see that, oh, it's done a pretty good job. Look at that, 17 in each leaf node. Each leaf node is pure. Oh, wow. There are no, oh, here's an impure leaf node. So there's a few impure leaves. Here's one. Leaf node is the name for a node at the end that doesn't go anywhere else. Here's another one. So it had to stop in a few places. If we'd left it with default parameters, it would have tried to split that. But since it's less than 10 samples, it just stopped and applied the label of the majority class, which is benign. But it still did a pretty good, it was still able to split them pretty good. Okay, that seems to have paid a bit of a price for accuracy here, although we'll run it again, 91%. So you have to do multiple runs and take the average of the runs with different testing and training splits to see how well it's really doing. Okay, the rest of them I'm going to let you guys experiment with, but here they are. So we tried max depth, min sample split. Splitter doesn't really change the algorithm, so you shouldn't really include that splitter equals random unless you're finding it's taking too long. Then you could maybe use that. Min samples leaf is the minimum number of samples required to be at a leaf node. So the minimum number is usually 1, meaning you're allowed to have a leaf node at the end. You're allowed to classify all the way down to just one example in the area. But if you set that to 10, then it's gonna say you have to have at least 10 items to be a leaf node. You can't split anymore after that. So it's a slightly different way of saying this. Yeah, some of these I'll let you guys look at them. You can also limit the number of features it uses. So here it's going to have to do a little bit of magic as well. But you can say, I don't want to see you use more than 2 features or 3 features. And then it's going to have to go through and try a few things and find the best small set of features to use when looking for the best split. Yeah, and I'll let you look at the other ones. Oh yeah, you can limit the number of leaf nodes, etc., etc. I'll let you look at the rest of them yourself. Okay. Then down here, these are the methods. So fit and predict are the 2 that we're using, but there's a few other methods here that you can take a look at as well if you want. And once the object is created, there are there's information that you can pull out of it. So the maximum number of features that it used, number of classes, and so on. But that stuff's not that interesting for what we're doing anyway. Okay, so that's the basic idea, is you're going to create code that looks a lot like this. You're going to have to put everything in a big loop in the assignment because you're going to do things more than once. And you're going to try different values, or maybe you won't put things in a... No, you will put things in a loop because you'll try like 5 or 10 different times. Make an array of the results, and then take the average of those results, and then you'll try again. And the only real difference in the next attempt will be the parameters that you put in here. Sorry about that. Someone's calling me. Okay, we're back. So that's everything that I wanted to tell you guys, is that you're going to need to try a different bunch of these parameters. And by the way, you may have noticed when I was going through this that there's nearest neighbor code in here as well, but remember, you're not to use this code. You're not to use the nearest neighbor classifier that's built into SKLearn. You have to create your own. Although you could use the nearest neighbor code that's built in to see if to compare to your nearest neighbor code. That would give you a sense of how well the thing's doing. So if your nearest neighbor code is getting 60% accuracy and that feels low, try the SKLearn nearest neighbor code. If it's getting about the same, then you know your code's probably okay. But if it's getting 80%, then maybe there's something wrong with your code. So that's something you can do. There is one more thing I wanted to show you, which is, you remember this thing that I showed you here? Let's see, just let it come up. This was a demonstration of the regions that k-nearest neighbor sort of divides a sample space into. So this is the iris data boiled down to 2 dimensions, and I'm showing you how overfitting works here. So k equals 1, it's going to classify everything around here as green. So it's fitting very tightly the sample data, and as you increase k, it fits it more and more kind of loosely until you just have these relatively pure regions. So it's kind of generalizing a little bit more. Anything that goes out here now is going to be considered the green class, whereas before there were all these little areas that I would consider blue within that green area. So it doesn't mean it's necessarily doing better or worse, but it just means that you need to try different values of k to make sure that you're not overfitting your training data too much. I have similar code here, which I actually gave you this code. It's in the sample code for this week, called trees_graph. Same idea, same training data, but now I'm using the SKLearn decision tree classifier, and I'm changing minimum leaf size. So I'm throttling back. With min leaf size equals 1, it goes to 100% accuracy on the training data, and this is what the areas that it's forming look like. So I get this by defining a 100 by 100 range in here, and then passing in each of those points and graphing it on here, whether to see which class it got. As I increase the minimum leaf size, it sort of approaches. It stops being so idiosyncratic. It stops like being so. Like over here, again, just with k and n, over here near this green point, it's going to classify it as green. That goes away pretty quickly, as do some of these other little areas here. So we kind of end up with a kind of a pixelated version of the k-nearest neighbor code. Everything here is straight lines because of the way that we make straight line cuts through the feature space. But you can see that changing this parameter here, as well as some of the other parameters, has the same effect of causing it to fit the training data less and generalize more. So over here, it's getting lower accuracy on the training data, but it may possibly be doing better on the testing data because it's able to generalize and hasn't fit all the idiosyncrasies of the data over here. Okay, so that's what's going to go on in the assignment. I want you to read the assignment on your own. In the Zoom class this week, I'm going to debrief the activity from the last video, and I'm going to go over the assignment, and we'll talk about this code a little bit more if you need it. Okay, so I'll see you in class.